started for today. Okay, so let's now try applying the ideas of molecular polarity, molecular symmetry, molecular geometry to constitutional isomers. So this is a classic example of how constitutional isomers can have different properties, polarity, and reactivity. So in this example, let's try drawing three constitutional isomers for C2H2Br2. So what I'm going to do is I'm going to start us off with our first Lewis structure. I'll draw both the Lewis structure and the bond line structure. So we've actually drawn this Lewis structure in an earlier class session, and the first potential constitutional isomer looks something like this. Now, if we're thinking about the molecular shape and molecular geometry of each atom, what would the geometry be for each of these carbon atoms? What would the geometry be for each of our carbon atoms? What was that? Trigonal planar, exactly right. So if we're drawing this molecule with respect to its 3D shape, it's perfectly flat, and we're already respecting the bond angles found in this molecule. And what is the bond angle for a trigonal planar geometry? 120 degrees. That's why we've drawn our bonds separated with a 120 degree bond angle. Now let's think about our bond polarity. Let's think a little bit about our bond polarity. Which bonds are polar in this molecule? Yep, the carbon-bromine bond. And what direction will this dipole point? What's more electronegative, carbon or bromine? Bromine, yep. So we're going to draw our dipole pointing towards bromine. Perfect. This other carbon-bromine bond is also polar. It's a polar bond. If we think about our next dipole, where are both of our dipoles pointing? Up or down? Are they pointing in a direction? Down. So then, is this specific constitutional isomer considered polar? Yes. Now, what I'd want you to do now is to play around and write out two other constitutional isomers. Same. So I'd like you to write out a constitutional isomer as well as what would be called a stereoisomer. So same number of atoms, but different relative connectivity. And you'll see one of these two structures that you draw is completely nonpolar. So try first drawing out two isomers, one constitutional, one stereoisomer, and try and assess if there is a non-polar isomer for this compound. That's good. Everything going okay? Everything going okay? Yep, that's good so far. Everything going okay? It's good so far. Everything going okay? Mm-hmm. Yep. Looks good. Now, are those arrows in the same or opposite direction? Opposite. So will they cancel? Yep, exactly. Yep, looks good. So, the Lewis structure portion of this exercise is important, but it's not our centerpiece. If we want to quickly generate isomers for this specific compound, what's our rule? What do we swap? So I'm going to circle my bromine, and I'm going to circle a hydrogen. If I want to quickly generate an isomer, and a plausible isomer, all I have to do is swap my functional group with a hydrogen, right? That's our trick that we learned previously for generating a pool of plausible isomers. So the first isomer we can draw has both of our bromines attached to the same carbon. Now, we're already respecting our molecular geometry because I'm very attentive and I've drawn out my bonds separated by what bond angle? 120 degrees. Okay, let's now take a moment and let's take a look at our bond dipoles, and let's switch colors for that. Okay, we've established our carbon-bromine bond is polarized towards bromine. So where are both of our bond dipoles pointing? To the left, right? So since we have a net molecular dipole, is this molecule polar? Yes, it is polar, has a net dipole. Let's draw our third potential isomer, and this isomer is known as a stereoisomer. In this case, we have our bromines on opposite sides of our carbon-carbon double bond. We call this the trans stereoisomer. Stereoisomers have different what? Stereoisomer, what was that? Yes, different shape. So these two species are stereoisomers. Now, this specific stereoisomer is quite interesting. If we look at this trans stereoisomer, we see something really cool when we look at our bond dipoles. So drawing out our bond dipoles, our carbon-bromine bond is polarized towards bromine. And if we look at our dipoles, are they in the same or opposite directions? Are they pointing in the same or opposite directions? Opposite. And since they're the same magnitude, will these dipoles cancel? Yes. So we have no net molecular dipole, and this is the non-polar isomer for this molecule. So this is really connecting this idea that isomers, both constitutional and stereoisomers, have different properties and different potential reactivities. Does that make sense to everyone? So you may see something similar to this on one of your exams. Okay, let's now talk a little bit about the nature of chemical bonds. Let's really get to know what makes certain bonds stronger than others. So first and foremost, a chemical bond is shared electrons between atoms. So for example, if you have a hydrogen-hydrogen single bond, we are fundamentally sharing electrons between the nuclei of two atoms. From the perspective of valence bond theory, a chemical bond is the result of overlap between half-filled atomic or hybrid orbitals. So you can draw this exact same interaction as a hydrogen 1s overlapping with a hydrogen 1s, leading to a bonding molecular orbital, or a sigma 1s plus 1s orbital. Both interpretations are valid and both are reasonable ways of looking at bonds. Okay? Now, why do we form bonds? When we draw this H symbol, what are fundamentally found at the center? What are found at the nucleus of every single atom? Protons, yes. And as we've discussed, electrons are negatively charged, right? And do opposite charges have a stabilizing effect when they're brought in proximity? Are electrons stabilized by protons? Yes. So in general, we definitely want to place our bonding electrons shared between the nuclei of two atoms because this is a stabilizing interaction. Electrons are lower in energy when they're shared between the nuclei of two atoms in general. Okay, now let's talk a little bit about bond strength and bond energy, since we can measure this using thermochemical techniques, just like we talked about in Chem 101, or that was discussed in Chem 101. So bond energy, bond enthalpy is a really useful term for getting a sense of how much energy does it take to break a bond. It's the energy required to dissociate a bond into its component atomic elements in the gas phase. We're not going to worry too much about the specifics of why it's in the gas phase. It's just these are the tabulated values associated with bond energy measured for a range of different compounds. And it gives us a sense how strong are certain bonds, how weak are certain bonds, and how labile, how reactive are certain bonds potentially. Okay, bond energies are positive. It costs energy to break bonds. That's the key takeaway here. Why? The electrons are more stable in a bond. Okay, is everyone clear on what bond enthalpy bond energy represents? Because you often see these referenced in your textbook when they talk about bond strength. Okay, so let's now talk a little bit about when does bond energy increase? What are the criteria for observing a large bond energy? Okay, so bond energy increases with, and this is in order of importance. First and foremost, bond order. Your triple bonds are stronger than your double bonds, which are stronger than your single bonds. So for example, if we compare the carbon-oxygen bond in carbon monoxide versus the carbon-oxygen bond in formaldehyde versus the carbon-oxygen bond in dimethyl ether, what is the strongest carbon-oxygen bond for this set? The single, double, or triple? Triple, exactly. And this is just due to bond order. The more electrons we share between our two atoms, the stronger our bond, right? Because how many electrons are shared in this triple bond? How many electrons total are we sharing? 6. So that's a much stronger electrostatic interaction than these 2 electrons shared in our single bond. Does that make sense? Okay. Now, this is where we start to end up with terms that are closely entangled. In general, for bond length, shorter bonds are stronger. In general, the closer your sharing of electrons between atoms, the stronger your bond. Another interpretation that you can think about from this perspective is that shorter bonds result from the overlap of lower energy orbitals closer to the nucleus. And if we're using lower energy orbitals to form our bonds, if we're using low energy orbitals that are closer to the nucleus that result in a shorter bond, what's going to happen to our bond energy? Is our bond energy also going to be lower in energy? Yes. So this in turn leads to a lower energy bond. Okay, so to show this pictorially, if we have carbon as our neutral party, so carbon is going to be the same atom that we're going to use to form a bond in both cases. So carbon is going to use, let's suppose it's going to use an sp3 hybrid orbital. And it's the same sp3 hybrid orbital in both cases, right? Same carbon atom, just for a reasonable comparison. Now, I'm going to draw my first example of fluorine. Now, fluorine, it's going to use a 2p derived orbital. So would you expect that orbital to be relatively small or relatively large for n is equal to 2? Small, right? So we'll draw the overlap. It's relatively small, short bond, close to the nucleus. These 2 orbitals are overall relatively low in energy. Now, to showcase the difference in energy between a fluorine 2p orbital and a chlorine 3p orbital, let's showcase the difference in orbital size and how that affects our overlap. So if we draw chlorine, and this time I'm drawing it a little bit farther away, is our orbital going to be larger or smaller? Chlorine, larger, right? So we're going to draw a larger orbital. And as we notice, because chlorine is using a larger orbital, is our overlap going to be as efficient? Are we going to end up as strong of an overlap between our two orbitals and as strong of a sharing of electrons between our two atoms if chlorine has its orbital just stretched out so far away from its nucleus? No. So this is a weaker overlap. And because we're using orbitals farther from the nucleus, this is a longer bond. So in general, the longer the bond, the weaker it is in most cases. The reason why I like the orbital interpretation is it can explain some of the exceptions that occur. And the reason why this longer bond is weaker is because this orbital energy is larger, so our bond energy is going to be larger. It's going to be a weaker bond, less stable bond. The last main criteria for bond strength has to do with bond electronegativity and polarity. Polar bonds in general are strong because they have more pseudo-ionic character. And let's showcase what I mean by that. Let's showcase what I mean by pseudo-ionic character. So if we look at a hydrogen-fluorine bond, just from our basic Lewis structure perspective, what atom is more electronegative? Fluorine, right? So fluorine is going to have an absolute ton of electron density, while poor hydrogen is going to have a very small amount of electron density, right? Now, as a result of this uneven distribution of electron density, as a result of this polar bond, my question to you is, what kind of charge will build up on fluorine? Partial negative, right? And hydrogen will have a partial positive charge. Now, as we've learned in ionic compounds, do these opposite charges experience an attractive interaction? Do opposite charges attract? Yes. So then, this attractive interaction between our two partial charges results in a pseudo-ionic bond that's stronger than your typical covalent bond. So polarized bonds are stronger than nonpolar bonds. Assuming equivalent factors in other cases. As you notice, this is third on our list of factors that affect bond strength. So this is not the most important, but it does come up. This is why a hydrogen-fluorine bond is substantially stronger than a hydrogen-oxygen bond. And my question to all of you is, if we look at this hydrogen-oxygen bond, will there be as much electron density polarized towards oxygen? Is oxygen as electronegative as fluorine? No. So then we still generate a delta minus, but I'm going to draw it a little bit smaller just to reflect the fact that, so it's like tiny delta minus, smaller delta plus. So your bond is less polarized, so overall it has less ionic character, and it's in turn a slightly weaker bond. Does that make sense? This is a relatively minor factor, but it does come up. Any questions on these factors? Okay, let's now talk a little bit about bond length. So, we discussed previously the reason why bond strength increases with bond order. Essentially, triple bonds involve sharing 6 electrons. And to break a triple bond, you have to separate your 6 electrons between atoms. So for example, if we take a look at a carbon-carbon triple bond, such as that found in acetylene, we have a substantial amount of orbital overlap between our two atoms, right? We have, in this triple bond, how many total bonds do we have? How many sigma and pi bonds? 2 pi bonds and 1 sigma, right? So we have this sigma bonding orbital sitting in the middle of our two atoms. And additionally, we have a total of 1, 2 pi bonds. So due to the fact that we're sharing a substantial amount of electron density between atoms, triple bonds are quite strong. Does that make sense to everyone? Just to reiterate that point. Now let's talk a little bit about why does bond strength increase as bond length decrease. So let's summarize our findings. So first and foremost, electrons in shorter bonds are held closer to the nucleus, and so they get a greater stabilizing effect from the nuclei, right? They're closer to the nucleus, so they get greater stabilization. That's the same reason why orbitals in atoms with a smaller atomic radius are lower in energy. Now, short bonds are also the result of close overlaps of orbitals close to the nucleus that are low in energy. So if you're using low energy orbitals, you're going to get a lower energy bond, or lower energy bonding orbital to be exact. Now, in general, electrons in short bonds are lower in energy, and as such, it takes more energy to break these short bonds. You have to put more energy in. Let's now look at some factors that affect bond length. And let's really drill down on orbital effects on bond length and strength. Okay, so as we've discussed, bond strength and bond energy is based on the relative energy of the orbitals used to make a bond, right? Your orbital energy affects your bond energy. So for hybrid orbitals, when we discuss the different hybridizations, what hybridization produced the lowest energy hybrid orbitals? What are the lowest energy hybrid orbitals? What hybridization? SP, exactly. So if we compare sp3, which is the highest in energy, sp2 is the next highest, and our sp hybridization is the lowest energy orbital hybridization. So your sp orbitals are lower in energy. Now, as a consequence of this, the consequence of this fact is that for bonds with the same bond order, bonds made using an sp orbital are lower in energy and stronger than bonds made using an sp2 or sp3 orbital. So your atom's hybridization affects the strength of bonds that that atom forms. So the reason behind this, sp hybridized orbitals have more s character, are lower in energy, and they're shorter. So any bonds involving an sp hybridized atom are shorter and stronger. Does that logic make sense to everyone? You're using a shorter, lower energy orbital, so your bonds are going to be shorter and lower in energy. Now, as a general rule, bond strength involving sp hybridized atoms is stronger than sp2, which is stronger than sp3, for the same bond order, of course. So where do we see this pop up? So let's take a look at a few pictures here. Let's look at ethane, which is CH3, and I'm going to draw out one of the CH bonds. So CH2H, CH2H. So if we look at this specific carbon-hydrogen bond, we see that the carbon-hydrogen bond strength is approximately 421 kilojoules. Okay? Now, I want you to pay attention in this chart to the CH bond strengths, because if we look down to ethylene, not looking at the carbon-carbon bond, but just looking at the CH bond, you'd say, oh, those are both carbon-hydrogen single bonds. What's the difference? Well, if we take a look into our table, this bond has a strength of 464 kilojoules. That's 40 kilojoules difference in bond energy. That is substantial. So why is there this difference? What's the difference between ethane and ethylene? What's the difference? What's the difference between the carbon atoms that lead hybridization? Exactly. So this is an sp3 hybridized carbon. Well, in ethylene, our carbon is sp2. Does that make sense to everyone? Okay, and that's because sp2 orbitals are lower in energy. Okay, any questions on hybridization effects on bond length and strength? Okay, let's keep going then. Oh, whoops. Yes. And so key thing, bond strength is represented as how much energy does it take to break a bond. So the lower in energy your bond, the more stable your bond, the higher this enthalpy. Yes, that's the energy required to shake off your electrons, break your bond completely. And the lower in energy your bonds, the higher the bond energy. Does that make sense? Yeah. Perfect. Okay. Let's now take a look at bond length. Bond length is relatively straightforward. Bond length decreases with, first and foremost, increasing bond order. So double and triple bonds are shorter. So for example, if we looked, for example, at the carbon-oxygen bond in something like methanol, and we compared it to a carbon-oxygen bond in formaldehyde, which of these two bonds would we expect to be shorter, the single bond or the double bond? Double bond. So the double bond is shorter. Okay. Additionally, when we discussed bond energy, we came on to this really key point. The smaller the atomic radius of your atoms, the shorter your bond length. And just to redraw that picture, if we think about HF, our orbital overlap let me draw this to scale. So for fluorine, we're using a 2p orbital. If we compare that to a hydrogen-chlorine bond, chlorine's orbital is going to be larger or smaller? Larger. Okay? So let's draw this to a bit of a comical scale, really just to make this point. Because chlorine is using a 3p orbital, is this interaction, is this orbital overlap going to be as close to the nucleus for each of these atoms, or is it going to be, are the atoms going to be farther away because our orbitals are farther away? Yep. So overall, if we have a larger atom, that in turn leads to a longer bond. I always like to think about things from an orbital perspective. Okay, just as a side note, just to recap atomic radius trends, atomic radius increases as you move down a group and as you move to the left across a row. So I like to think of radius increasing as an arrow going down and to the right. This can be explained from the perspective of orbital size, thinking about as you move down the periodic table, what happens to your outermost orbital shell? Is it going to be larger or smaller? Larger. And what happens as we move to the left? What are we decreasing as we move to the left? What do we have less of if our atomic number gets smaller and smaller? Less protons. So the reason why your radius increases as you move to the left, you have less protons, so your electrons are less closely held to the nucleus, so your electrons are farther away from the nucleus. There's a weaker attraction of our electrons pulling them in. Okay, any questions on, yes?
So would a triple bond be shorter than a double bond?
Exactly right, exactly right. Yep. And that stems from the fact not only are you using an orbital that's shorter and closer to the nucleus, but the fact you have more electrons shared between your two atoms means overall there's a greater attractive interaction and in turn a shorter bond. Does that make sense? Perfect. Any other questions? Let's keep going then. So what I want us all to do is take a moment and circle from these two choices which bond is shorter. So I'll do the first one. If we look at a nitrogen-oxygen double bond versus a single bond, what types of bonds are shorter? What happens is you increase the bond order. Do your bonds get longer or shorter? Shorter, okay? So the NO double bond is shorter. I'd like you to attempt these next two examples, and then we'll come together as a group to discuss. So then what has the smaller set of atoms? Yes. Yep, and it's also small. Yep. So because we compare fluorine and bromine, fluorine is smaller. So just to discuss bond length, in general, if we have a smaller atomic radius, is our bond length going to be shorter? Yes. So which of these two atoms, bromine or fluorine, has the smaller atomic radius? Fluorine. Okay. Now in this third example, we have to consider not only bond polarity, but atomic radius. So if we compare bromine versus fluorine, is bromine substantially larger than fluorine? Yeah. So then, which of these two bonds will be shorter? The one involving the smaller fluorine or the larger bromine? Smaller fluorine. Okay, let's now do these next set of examples together. Let's take a look and let's try to identify which bond is stronger. So in general, what bond is stronger, a single or a double bond? Double bond. Okay, if we compare a nitrogen-oxygen to a nitrogen-fluorine bond, so in terms of bond polarity and bond electronegativity, as well as atomic size, what atom is smaller and more electronegative? Yep, fluorine is smaller and more electronegative, so it has the shorter, stronger bond. Does that make sense to everyone? Okay, let's look at one last example. This is really relevant in organic. Which of these two bonds is stronger, a carbon-hydrogen or a carbon-carbon? What has the smaller atom, smaller, lower energy orbital? Carbon-hydrogen. A carbon-hydrogen bond is very, very strong. It's very difficult to react, unactivated carbon-hydrogen bonds. Does that make sense to everyone? This is really just getting us used to the idea of assessing bond length and strength, because this helps us assess the reactivity of bonds. Okay, let's keep going then. So let's take a look at formaldehyde and carbon dioxide, and let's just do a basic analysis asking which bond is stronger, the carbon-oxygen bond in formaldehyde or the carbon-oxygen bond in carbon dioxide. So take a moment, write out the structures, and tell me which of these carbon-oxygen bonds is stronger. Everything going okay? I think so. Okay. Everything going okay? Everything going okay? Oh, carbon is right. So everything going okay? So which carbon oxygen bond is stronger? Think about hybridization. Try writing the hybridization, so let's see which one has more S character. So I've seen a lot of reasonable responses. Let's first draw out each of these two structures. Now, this may seem like a relatively innocuous question, but you have to look at all the factors involved when deciding which bond is stronger. So, with both of the Lewis structures for formaldehyde and carbon dioxide written out, let's write the hybridization. So for formaldehyde, what is our hybridization of this carbon atom? sp2, yep, because it's formed a total of 3 sigma bonds and 1 pi bond. What is the hybridization of the carbon in carbon dioxide? sp. So, as we discuss the effect of hybridization on bond strength, which of these two carbon-oxygen bonds uses lower energy, shorter orbitals? What? sp. So then, this carbon-oxygen bond in carbon dioxide is stronger and it's shorter. And that's driven by the hybridization and what orbitals are used to form our bond. Does that make sense? Yes.
So that means that they're less likely to react or more likely to
it requires more energy to break that bond. Okay. Yeah. So it doesn't necessarily say they're less likely to react, but it just has a greater energetic cost. Yeah. Does that make sense? Perfect. Any questions on this example? Let's do one more of this type, just to make sure we're comfortable assessing hybridization. And this one, I would really put a star next to as an interesting case, not only of assessing hybridization, but also thinking about potential resonance effects. So comparing C2H4 and C2H6, so let's draw out both of these structures. So the first is ethylene, the second is ethane, and just like before, whenever you're thinking about bond strength, we first have to identify the hybridization of each atom involved in our bonds. So what's the hybridization of the carbon atom in ethylene, the carbon atom on the left? sp2. Exactly right. Exactly right. Oops, let me change pen colors. Okay, and what about the carbon atom in ethane on the right, the structure on the right? sp3. Okay, perfect. So then, if we think about our two carbon-hydrogen bonds, which bond is going to be lower in energy? Which bond is formed using a lower energy orbital? sp2. So this carbon-hydrogen bond in ethane is going to be shorter and it's going to be stronger. Does that make sense to everyone? Okay. These kinds of hybridization effects can't be understated. Okay, let's keep going then. So, particularly relevant today, let's take a moment and let's discuss a little bit intermolecular forces and phase changes. So, how do the properties and polarity of our molecule and the functional groups in our molecule affect their physical properties, such as melting point, boiling point, vapor pressure? So, the melting and boiling point of a substance are closely tied to the strength of interactions between molecules, okay? So melting point and boiling point can give us some insight into the relative strength of different intermolecular forces. So strong intermolecular forces, strong interactions between our molecules lead to higher melting and boiling points, lower vapor pressure, and larger viscosity. So you can observe this quite clearly if you compare two different liquids, as you'll do in this current class session in laboratory. And you'll see that depending on their structure and the strength of their intermolecular forces, they boil at different temperatures, right? Structure impacting properties and functions. Intermolecular forces also control solubility, miscibility, and other bulk properties. So we're going to break down some of the common intermolecular forces, as your goal in this class is to use and assess the strength of intermolecular forces to get a sense of and start to predict the properties of our molecules. Yes? Miscibility is mixability. So miscibility is how readily liquids mix. Mix to form a homogeneous solution. So it's like the idea that alcohol and water mix in certain ratios. And once you have too much of one component, they no longer mix efficiently. Okay, so now that we've introduced what intermolecular forces actually do in terms of affecting substance properties and functions of materials, let's talk a little bit about our intermolecular forces, and let's summarize the reason how each of these intermolecular forces function. Now, your most general catch-all intermolecular force that is found on any material, any substance with electrons, are known as London forces, also called dispersion forces, also called van der Waals forces. There are many names, and depending on when you're taught chemistry, you'll have a different preference for the preferred name. These are temporary dipole-dipole interactions. So what does that mean? This is a weak interaction between temporary dipoles formed from the random movement of electrons and changes in electron density from molecular collisions. So these are random events where a temporary dipole is generated. Dispersion forces are unique in that they occur between all types of molecules. If it has electrons, it can experience dispersion forces. It increases in strength with the number of electrons, molecular weight, and most importantly, and what's often not addressed thoroughly, the number of atoms, just the number of atoms, period, in your molecule. Now, these forces heavily depend on molecular shape. Molecules that are compact with less atoms have weaker London interactions. So we'll talk more on how this affects both linear and branched boiling points. So to give you a picture of how London forces function, suppose you have two nonpolar molecules, right? There's no uneven distribution of electrons, right? So your electrons are sitting evenly, shared in bonds, or sitting on each individual atom, depending on your perspective. At any given time, your electron density could, through the random motion of electrons, end up piled up disproportionately on one side of your molecule. So as we're showing it piling up on the left-hand side, suppose your electron density ends up localized on one side of your molecule. Due to this random movement of electrons, we have generated a set of temporary dipoles. And as there is a temporary separation of charge, we in turn have a series of partial charges. Now, these partial positive and partial negative charges that are temporarily generated, can they attract? Do these opposite partial charges attract? Yeah, and this interaction between temporary dipoles is stabilizing. This is an intermolecular interaction between two molecules. Does that make sense to everyone? Okay. These are very fleeting events. These occur in the fraction of picoseconds to nanoseconds. These are not very long-lived. And that's why they're so weak, because they're so short-lived. Let's, as organic chemists, start to take a look at structure and how it affects function. Let's take a look at London forces and molecular size. And this is the best picture I can come up with to explain this idea of why longer molecules with a larger number of atoms have stronger London forces. So in general, as molecules get larger, dispersion forces increase. So your larger molar mass means you have more atoms, which means you have more electrons. And if you have more electrons, can you move these electrons around to generate stronger temporary dipoles if you have more electrons to work with? Yeah. So larger molecules have stronger London forces, and in turn, these interactions between molecules drive up your boiling point. Because your molecules are interacting so strongly, it's harder to pull them apart. Right? So, for example, if you have your molecules sitting around in solution, it's harder to coax this molecule to go into the gas phase if it's firmly interacting with and engaging in strong interactions with other molecules in solution. Now, keep in mind in these two pictures, what's a major difference between the small and the large molecule? Do you notice a difference in not only the number of electrons, but what else? What else is different about these two? Surface area, exactly right. So this larger molecule, I just want you to notice, it has also a larger surface area and number of atoms. So it's not just the number of electrons, but it's how many atoms do we have to distribute these electrons over? Because the greater the area of interaction, the stronger the interaction. Has anyone ever played with Velcro or duct tape? If you use a really long piece of duct tape and you stick two pieces of paper together, is it harder to pull them apart? Yeah. You have a greater area of interaction, so a stronger interaction as a result. Does that make sense? Okay. So let's take a look at some hard data here. I would pay attention to this when you're writing your report for the physical properties lab, as this sort of helps answer one of the questions in your report. Larger molecules have stronger London forces and larger boiling points. So can't understate that. If we look at boiling point as a function of molar mass for our linear alkanes, just containing non-polar bonds, these are all non-polar molecules. What do we notice as our molar mass increases? What happens to our boiling point? Just looking at this chart. Increases. As our molar mass goes up, we have more carbon and hydrogen atoms. Our boiling point increases in almost a strictly linear fashion. So we see a direct effect on molar mass to the strength of London interactions, and we can see this by an increase in boiling point. Let's really just emphasize this idea of molecular shape, as you'll see some very interesting results with molecular shape and intermolecular forces when we observe cyclic molecules. So intermolecular forces fundamentally are based on the distance between molecules, right? An intermolecular force requires your molecules to be in close proximity, right? So then, the closer your particles are packed, the stronger your intermolecular force, assuming, of course, we're dealing with the same type of interaction. Now, where does this come up? Where does this idea of distance on intermolecular forces come up? Well, when you deal with linear versus branch shapes, what we found is that molecules with ordered linear shapes, so we call these saturated structures, they can pack more closely together, and in turn they have stronger intermolecular forces. So to define out what I mean by a saturated hydrocarbon, it's a structure containing primarily carbons and hydrogens with the maximum amount of CH bonds. An example of this kind of species would be ethane. which is CH3, CH3. You just have carbons and hydrogens, no double and triple bonds, just a simple, straightforward molecule. Now, when we compare linear molecules drawn in line notation, they look something like this. When we compare linear molecules to what we call branched or irregularly shaped molecules, when you have branching, so let's suppose we have some branching, and we try to pack multiple molecules on top of each other. We try to pack molecules in close proximity. Are these branching groups going to create issues packing our molecules close together? Do these branching groups limit how close we can bring our molecule? Yeah. So as a result, would we expect our intermolecular interactions between these branched molecules to be stronger or weaker? Weaker. So then would you expect branched molecules to have larger or smaller boiling points? Smaller. The boiling point is proportional to the strength of intermolecular interactions. We have weaker interactions, so it boils at a lower temperature. So we have weaker intermolecular forces, and I just want you to write lower boiling point. Okay. Now there's one other type of molecular shape that's really interesting, and we see these a lot in organic chemistry. So, as molecules become more flat or linear, your dispersion forces get stronger. Think about this from the perspective of surface area. If you have more surface-to-surface contact, you have stronger attractions. So if we compare a linear structure to a branch structure, let's take a look. We have the same number of atoms, but let's look at their boiling point and see if we notice a difference. So if we compare N-pentane, which is the linear species, notice how if we overlay two molecules together, is there a large amount of surface area overlap between these two molecules? Is there a strong, attractive interaction between these two molecules? Yeah, there's a pretty large surface area overlap. So we see our boiling point is around 36 degrees Celsius. Now, if we take the same number of atoms and we rearrange them to make a branched structure, such as neopentane, is there a large or small surface area? Small. So what would we expect to happen to the boiling point? Would it go up or down? Down. And as we see, the boiling point for neopentane is almost 27 degrees less. So it's a substantial drop in boiling point driven by what factor? What do we call this? Molecular structure and shape. Shape. So I just want you to really focus on the idea that shape is the driving force behind this difference in boiling. Okay, let's now continue on and let's look at another type of intermolecular interaction and another type of very special case. So when we talk about cyclic compounds, what do I mean by cyclic compounds? It means our carbons are arranged in a ring arrangement. So the most common one that we'll see is the hexane ring. If we compare cyclohexane to N-hexane, we observe that the cyclic structure has a substantially higher boiling point. Now, I'm going to mention this because you'll see this in laboratory, in your laboratory experiments, that your cyclic structures will boil at higher temperatures. We're going to leave this idea in the back of our mind, and we're going to come back to it in chapter 4 when we discuss cyclic structures, because it's a little bit hard to see with our current information tool set. But I just want you to know cyclic compounds have stronger interactions and boil at higher temperatures than your linear compounds. And it's partially driven by packing efficiency, but it's also driven by an additional effect. Yes. So like how readily can we layer multiple molecules close together? And so, for example, for linear molecules, their shape permits them to be brought close together to one another, and in turn provides a larger area for interactions between molecules. So when you have branch structures, that branching limits how readily you can bring your molecules close together, and it constrains and limits the surface area for this interaction to occur. Does that make sense? Okay, perfect. So just to make sure we're all on the same page, let's try to apply this idea to predict which of the two substances in each of these charts would have a higher boiling point. So let's take about a minute and a half. Let's work on this, and then we'll come together as a group to discuss. Everything going okay? Yep. So in our discussion of cyclic compounds, we generally have higher or lower boiling points. Everything going okay? Everything going okay? Yep. First one is good. Everything going okay? Which one would you expect? Yep, exactly. Yes, exactly. So let's talk a little bit about each of these examples. In the first case, which of these two molecules has a larger molecular weight? The one on the left or the one on the right? Right. Okay, perfect. So we'd expect it to have a higher boiling point. Now in this second example, we're comparing a linear structure to a cyclic structure. And in general, where do we observe larger boiling points? Linear or cyclic structures? Cyclic, okay. Perfect. Any questions on London forces and factors that affect the strength of London forces? Okay, let's look at another intermolecular interaction, and let's look at another set of compounds, and let's try to see which substance would we expect to have the larger boiling point, or the larger boiling point. So let's compare iodine and chlorine. So thinking about it, which of these two species has a larger molar mass? Iodine. So which species would you expect to have a larger boiling point? Iodine. That's why iodine's a solid and chlorine is a gas. Comparing nitrogen and argon, which species has the larger molar mass? If we compare nitrogen and argon. So nitrogen mass is approximately 28. Argon's mass is approximately 40. Argon wins out. And then finally, just looking at a condensed formula, comparing C5H12 versus C6H14, which of the following has the larger molar mass? Which has the longer chain? Yes. Yes, you can assume that they're linear. C6H14. Yeah, larger molar mass, longer carbon chain, stronger London interactions, larger boiling point. So I just want to get you in the habit of looking at a formula and estimating boiling point. Okay, let's now take a look at the next type of intermolecular interaction, which is dipole-dipole interactions. So dipole-dipole intermolecular forces, as their name implies, are an interaction between molecular dipoles of two polar molecules to give strong attractive interactions. So what types of molecules do we observe dipole-dipole interactions for? Polar molecules. Okay, from a molecular picture perspective, there are regions that are delta minus and delta plus in our molecules, and those regions with opposite partial charges, are they going to attract or repel? Attract. Again, opposite charges attract is really a wonderful rule that governs the majority of the discussions that we're going to have in organic, just like charges repel. You may see us repeating these phrases a lot. Now, these dipole-dipole interactions, they increase with dipole strength. So for example, looking at a hydrogen-chlorine bond, is this bond substantially more polarized? Yes. So there's a much larger delta minus and a much larger delta plus. So what we would expect if we compared HCl, so looking at HCl, we would expect to observe very strong dipole-dipole interactions. Okay. So just always keep in mind that these interactions are driven by dipole strength. Now let's take a look at a few more systems, and let's take a look at the effect of dipole moment, which is a reflection of molecular polarity as a function of boiling point. So dipole-dipole intermolecular forces are much stronger than London forces. And in general, polar molecules will have higher boiling points. Now, these intermolecular forces, these dipole-dipole forces, increase in strength with dipole strength. So let's take a look at the following chart, which showcases boiling point as a function of dipole moment, which is a reflection of molecular polarity. And as we see, if we compare propane, which is non-polar, so propane is non-polar, and we move from propane to diethyl ether, we have not changed our molecular weight substantially, but what has happened to our boiling point? Has our boiling point increased? Yes. So just by going from a non-polar to a polar molecule, you see a jump in boiling point. Now, as we increase our dipole moment, as we increase our net molecular dipole, does our boiling point increase? Looking at as our dipole moment's going up and up and up, what's happening to our boiling point? It's also increasing. So more polar molecules have stronger dipole-dipole interactions, and as a result, they have higher boiling points. Okay. Any questions on that relationship? In general, the stronger your molecular dipole, the higher your boiling point. But notice, what did we keep constant in this experiment? Are all of our molar masses about the same? Yes, and that's the only way to really see this effect, because London forces are still also at play in all of these molecules. So if we tack on a huge amount of molar mass, that will cloud out this effect of dipole moment. Okay, let's keep going. And let's just take a look, and I'd like you to tell me what substance in each pair has the higher boiling point. So take a minute and a half to work on this, and as you see, our good old friend 1,2-dichloroethane pops up again. So take a look at that and tell me which of those substances has the higher boiling point. Everything going okay? Okay. Everything going okay? Yes. So which of these two would have the higher?
Well, I'm analyzing right now. So I see that this one's the same atom, the same side. So this will be more polar, right?
Yeah, because the dipoles are aligned in the same direction.
So this one would be the one.
Yeah. Any questions? Yes. Yes, exactly. There's a dramatic difference in the gold. That's how you can separate. Okay, let's talk about these examples. Now, one thing I have to make abundantly clear, the way these first two pictures is drawn is a little bit suggestive for what's actually going on. Can this carbon-carbon bond, can we just rotate this carbon-carbon bond? Can you rotate single bonds? Are they constantly rotating? So don't focus too much on the fact, oh, in this one they're on opposite sides, because this bond can rotate. Let's focus now on what atoms are each of these fluorines located. So in the case where the carbons are located, where each carbon has one fluorine, the fluorines are located on two different carbons. Our dipoles, in general, are pointing across the carbon-fluorine bond, but just remember, the carbon-carbon bond can rotate. So they're in rotation, there are moments when the dipoles are aligned, and there are moments when the dipoles are opposed. If we compare that to when both of our fluorines are attached to the same carbon, no matter how much we rotate our carbon-carbon bond, are both of our dipoles aligned in the same direction in the second example? Does that make, are both the dipoles pointing in the same direction in our second example? Yes. So then we would expect which of these two structures would have the stronger molecular dipole? The one on the right. So this structure has a stronger dipole. And as a result, what would happen to its boiling point? Would it be larger or small? Larger. Okay, let's look at this next example. We've already established in our previous work analyzing molecular polarity, which of these two stereoisomers, which of these two molecules with the same connectivity but different shapes, is polar. Which one of these two is polar? The one on the left. The cis isomer is polar. It has a net molecular dipole. So this molecule is polar. The trans isomer, the dipoles cancel, so it's non-polar. And if we have to compare a polar molecule to a non-polar molecule with the same molar mass, same molecular weight, which one of these two molecules has a higher boiling point? Polar, yep, by far. And that is why you can separate these two isomers by distillation. Yes?
So if they had different molecular weights, does it have to be an extreme difference to be considered stronger?
Yes, in general, all the examples that you're going to be comparing in this course, the molar masses will be pretty close to one another, because molar mass has a huge effect on boiling point. Even increasing the molar mass by 10 ratchets up the boiling point by roughly 3 to 5 degrees Celsius. So it's substantial. Does that make sense to everyone? And that's why we're able to make the comparison in this case, because the atoms are almost identical and the molar masses are identical. Okay, let's talk about one of the more important interactions. This is often a source of very interesting structural features in molecules, and this intermolecular force is known as hydrogen bonding. I really want you to pay attention and always be on the lookout for hydrogen bonding effects, as it's often the reason why certain molecular conformations, certain molecular shapes, certain ion formations, certain ionizations are favorable. Hydrogen bonding is a very strong intermolecular interaction between a highly polarized hydrogen atom and an electron pair on an electronegative atom. So the way that I like to think about it is that we're dealing with a ZH bond. Let me switch pen colors for this. Okay, so a ZH bond where Z is nitrogen, oxygen, or fluorine. And why are we concerned with these three atoms? Why? What's so special about these three atoms? Are they electronegative or not very electronegative? Yeah, these are highly electronegative atoms. Okay, so we call the hydrogen bond acceptor the lone pair on nitrogen, oxygen, and fluorine. So the acceptor is this lone pair. As a corollary to the hydrogen bond acceptor, the hydrogen bond donor is the hydrogen bound to the ZH bond. So for example, if we're looking at a nitrogen-hydrogen bond, this hydrogen atom would be the hydrogen donor. Now, the reason why a hydrogen bond is so strong is that it has a large amount of electrostatic character associated. You can draw a hydrogen bond as a series of dashed lines, such as between a hydrogen on oxygen and a lone pair on oxygen, or you can draw it as a series of dotted lines. Both are fine. Now, the reason why a hydrogen bond is so strong is if you have such a largely electronegative atom, is it going to have a large partial negative charge? Yes. So this oxygen, this delta minus is gargantuan, has a lot of electron density. Likewise, this poor hydrogen bound to oxygen, if it's bound to a really electronegative atom, is this hydrogen going to have very much electron density? No. So it's going to have a really large delta plus. So you have a really, really small hydrogen atom that's nestled up and able to get really close to a really localized lone pair, a lone pair on a very electronegative atom that has a large amount of partial negative charge. So as a result, this delta minus, delta plus interaction, is it going to be strong or weak? Strong. A hydrogen bond is essentially a very, very, very strong dipole-dipole interaction. And it's uniquely effective because oxygen, nitrogen, and fluorine, are they large or they're small? Are they high up on the periodic table or low? They're small, right? So you have a small anion, a small cation, and they can get really close to each other and lead to a very, very strong interaction. Does that make sense? Always be on the lookout for hydrogen bonds, and it only occurs for ZH bonds, oxygen, nitrogen, and fluorine to a lesser extent. We don't often see hydrofluoric acid handled in the organic lab because it's not a fun reagent to handle and it's quite dangerous. And it doesn't have a lot of utility. Does that make sense to everyone? Okay. So let's, as our last set today, let's talk a little bit about hydrogen bonds. So hydrogen bonds are stronger than dispersion and dipole-dipole forces. So substances that can undergo hydrogen bonding have higher boiling and melting points. Now, just to put this into perspective, these intermolecular forces are still weaker than bond strength. They're much, much, much weaker than the strength of a chemical bond. But these intermolecular forces do have an effect on molecular properties, such as melting point, boiling point, viscosity. Now, one thing that you need to make note of, you need both a hydrogen bond donor and an acceptor to form a hydrogen bond. And the donor and acceptor don't necessarily have to belong to the same molecule. So for example, water can form hydrogen bonds because it contains both a ZH bond and a lone pair on an electronegative atom. So as a result, water has an uncharacteristically large boiling point. How many hydrogen bonds can water form? How many donors and acceptors does it have? 2. it has, let me point this out using a different color pen. 1, 2 hydrogen donors and 1, 2 acceptor lone pairs. So the fact that water can form 2 hydrogen bonds per molecule leads to a substantially higher boiling point than you'd expect. Does that make sense to everyone? Okay, let's continue on now. So I'd like you to tell me what has the higher boiling and melting point, ethanol or dimethyl ether? So let's take about a minute on this and then we'll come together as a group to discuss. And try to focus on explaining why. Any questions? Yes. So to help everyone along with this process, let's take a look at each of these Lewis structures and I'll draw them out for our reference. So we have CH3, CH2, OH, and dimethyl ether is CH3, OCH3. Now, when we compare these two compounds, is there any key features of ethanol that come to mind? Yep. They have the same number of hydrogens. They have the same molar mass. Do we see any specific bonding motifs that we need to be aware of? Yep. So we have an OH bond. We have an alcohol. And alcohols contain an oxygen-hydrogen bond, and the oxygen has 2 lone pairs. So what this means is, can ethanol form hydrogen bonds? Yes. So since ethanol can form a hydrogen bond, that in turn leads to a higher boiling point. Does that make sense? Okay, let's skip over this next example and let's start to look. We're going to skip over ion dipole forces as they don't often come up substantially. And let's take a look, and in the last few minutes, let's do some examples where we compare different molecules and assess the strength of the intermolecular forces. So let's start off with this first example. Which of the following compounds has a larger boiling point? So what's the main difference between these two compounds? What's the main difference between these two compounds? Shape. So in general, if we compare a branched structure to a linear structure, which structures in general have higher boiling points? Linear. So this structure is linear, so in turn has a higher boiling point. Okay, let's look at these next 2 examples. So starting off, we have a structure with 1 alcohol and a structure with 2 alcohols. Which of these structures can form more hydrogen bonds? The one on the right, right? So strictly counting, we can this structure can form 2 hydrogen bonds, and as a result, it has stronger intermolecular forces and a larger boiling point. Does that make sense to everyone? Now, this example we're going to have to pay a little bit of attention to. If we compare acetone to thioacetone, if we compare oxygen to sulfur, What's the main difference between oxygen and sulfur? So size and molecular weight, right? And which of these two atoms has a larger atomic mass, oxygen or sulfur? Sulfur. Okay, so thioacetone has a larger molecular weight. So would we expect thioacetone to have a larger boiling point? Yes, exactly right. Let's do one last set as our last activity for today. So let's compare acetone versus acetic acid. So let's compare a ketone containing molecule to that containing a carboxylic acid. And we'll begin to see a very interesting hallmark of carboxylic acids. So in acetone, what intermolecular forces do we have access to? What interactions do we have access to? Do we have a ZH bond? Do we have an OH bond? No. So what's the only intermolecular force we have? What was that? Dispersion and dipole-dipole. This acetone is polar, so we have dipole-dipole. Oops, one moment. So we see dipole-dipole. Now, in our carboxylic acid, in acetic acid, can acetic acid form a hydrogen bond? Does it have a hydrogen bond donor and acceptor? Yes. So it can hydrogen bond. So then, which of these compounds has stronger intermolecular forces and as a result a higher boiling point? Carboxylic acids. If you try to distill a carboxylic acid, you're not going to have a very pleasant time as they have very, very large boiling points due to hydrogen bonding. Okay, let's check these next two compounds. These ones are a real pain to work with. First is benzene, the second is phenol. So what's the difference between benzene and phenol? Can phenol engage in a unique intermolecular force? Yes, hydrogen bond. So phenol can hydrogen bond, in turn leading to a larger boiling point. Finally, and this is really getting at the idea of molecular symmetry and polarity. These two examples are ones that I'd like you to pay attention to, as this is the kind of nuance when we talk about polarity that you'll see in later chapters. So let's look at these two variants of dichlorobenzene. And let's draw out the bond dipoles. Since I want you to tell me which of these two compounds is most polar. And I'm going to give you a minute to try drawing out the dipoles. And just like we did with the dichloroethane example, try to look to see if the arrows are pointing in the same or opposite direction. So I saw a lot of reasonable responses, but can I get a show of hands? Who thinks the structure on the left is more polar? Oh, perfect. Structure on the right? Everyone. Good, good. So if we draw out our bond dipoles, thankfully this molecule is flat. As we notice, our bond dipoles point in the exact opposite direction. Yep. So is this dichlorobenzene derivative very polar? No. It's not quite zero, but it's very, very, very small dipole. Looking at this dichlorobenzene derivative, both of our bond dipoles are pointing in the same direction. So we have a large dipole that in turn leads to strong dipole-dipole interactions. Now, let's take this idea and let's apply it to a solvent system, okay? Using the exact same logic, looking at bond dipoles, comparing 1,4-dioxane and tetrahydrofuran, which of these two molecules is less polar, and as a result, you'd expect to have a lower than usual boiling point? Dioxane. And let's talk about why. Does everyone notice how dioxane has symmetry associated with its oxygen atoms? So if we think about our dipoles, the first carbon-oxygen bond dipole set is pointing towards the top half of our molecule. The second dipole set is pointing towards the bottom. They don't quite cancel out because this molecule has some 3D shape, but in turn, would we expect 1,4-dioxane to be very polar or slightly polar? Slightly. Yeah, so it's slightly polar. And as a result, it has a relatively low boiling point when compared to tetrahydrofuran. Why is THF more polar? If we look at our carbon-oxygen bond dipole arrangement, there's only one major dipole pointing towards the top half of our molecule. Okay, that's all I have for today. We'll be moving on to chapter 2 note set next class session. Please have that ready to go. This will show up a little bit later in your textbook than when I presented it, but I felt it's useful to talk about it now because we see the effect of hydrogen bonding when we talk about acid strength and base strength.